Hello everyone. So we are dealing with module 3, and that is deflection of beams, and that we have two methods to find out the slope and deflection of the beam. The first was moment area method, and the second is conjugate beam method. Moment area methods is already finished, that you can check out in the previous videos, and the next method, the second method, is conjugate beam method. Okay, so in this method, basically, we're going to do something with the supports. So now the supports, there are two types of beams here. One is the real beam, what is actually given in the problem, and the next is a conjugate beam. So we're going to take the real beam and convert into conjugate beam, and that's why it's called as a conjugate beam method. So in this method, what we do is, if you want to find the slope, that is theta, if you want to find slope of a given beam, that slope is found out using the shear force. So if you know the shear force of the beam, you'll get the theta, and if you know the bending moment of the beam, you'll know deflection. So the main important two things what you have to find out here is, to find theta you use shear force, and to find deflection you'll use bending moment. Okay, with this background, what we'll do here is, now there are two things I've told you. One is the real beam and the other is conjugate beam. So whatever in the given problem is the real beam, we're converting it into a conjugate beam, and hence because of the conjugate beam you have the conjugate supports. See here. So first thing is, you have to draw a conjugate beam. So conjugate beam is like a imaginary beam. Okay, so now you can check this out. This is the support of the actual beam. So this is the supports which are given in the actual problem. So what you're going to do here is, you have to we'll replace this support with the conjugate support. So that's why it's called as conjugate beam support. Now see here, in left end it's a fixed support, and that is in the actual beam. The same left end, in the left end, the same support gets converted into a free end in case of conjugate beam. Now see, the meaning of conjugate is like just the opposite. So if here it is fixed, see, left end is fixed, opposite to fixed is free, so that end we are going to free it. Likewise, now see here, left end support is free, so free in actual beam becomes fixed in conjugate beam. Okay, and similarly you can check this out. There is simply support and a roller support. Okay, now see here, this remains same in actual beam. If it is simply supported, in the conjugate beam also it is simply supported. In actual beam, if it is a roller support, in conjugate beam also it becomes roller support. Then you can check this out. Here it is a roller support. Now roller support or simply support, this will remain. You can see here, it is not exactly at the end, it is somewhere in the center. So if it is a simply support or a roller support, somewhere in the center but not the ends, so it remains as a hinge support. This roller support or simply support becomes hinge support, provided it is not at the end of the beam. Next, again here, roller support and simply support, again if they are not at the end, remains, they become hinges. These are called as hinge support. Okay, all right. So with this background, let us start with the problem. So it goes like this. So they've given you a simply support beam of span L, supports a central load of magnitude W, find maximum slope and maximum deflection. Again, it is a simple problem. They've just asked you maximum slope and maximum deflection. So because it is a simply support, we'll draw the first thing is, we'll draw the deflected shape of the beam. This is the actual beam which is given in the problem. Immediately below this, we'll draw the deflected shape of the beam. Again, deflected shape of the beam, it is drawn wherever there is a maximum load, there will be maximum deflection. And because the support, the deflected shape of the beam is like this. And to find below the load there is a maximum deflection, so I'll write this as delta, and because it is at C, so delta C, so this is the maximum load. Next, rotation. You can see here rotation, again this deflected shape of the beam. For that deflected shape of the beam, from this point draw a tangent, then this is theta A. Similarly, for the deflected curve, draw a tangent like this, so this is theta B. This is theta A and this is theta B. So if you find theta A, because it is symmetrical, it would be just the theta B would be just the opposite of that. So you're supposed to find theta A, theta B, those are slopes, and you have to find delta C, that is deflection. Okay, so the important thing here is, in this method, you have to always find the reaction forces. Always you have to find the reaction forces. Now you can see here, W is acting at C, which is exactly at the center. I just place it at distance L by 2 and L by 2. So this W, which is acting downward, because it is simply supported, downward load gets distributed equally here, to the left side and to the right side. Now this is like W acting downward, which gets distributed to the left and to the right, but upward. So that's why RA is W by 2, RB is W by 2. Okay, because it is symmetry, things become simple. Okay, it's like 1W acting downward. To stop this 1W, there are two forces which is acting upward. That is half W upward, half W upward. So when you add this, this becomes 1W upward. So 1W upward, 1W downward. The beam is in equilibrium. All right. So the reaction at A, RA and RB is W by 2. Next, when bending moment at A and bending moment at B is 0 because they are supports. And bending moment at C. Now, if you check this out, bending moment at C, either you can say to the left or to the right. Now, if you see to the left, so here only one force is acting, that is RA, which is W by 2. So here RA is W by 2. So if you see to the left side of C and you're finding the bending moment at C, so left side of C, RA, which is W by 2 into this distance. So W by 2 into L by 2. So it is WL by 4. So now bending moment at C is WL by 4. So after this deflected shape of the beam, you have to draw the bending moment diagram. It is same like the moment area method. First thing, you have to draw the deflected shape of the beam, then bending moment diagram. After that, M over EI diagram. So till this steps, everything is same, just like the previous method. So it is now WL by 4. After this, important thing is you have to draw the M over EI diagram. Again, the same beam, same diagram continues. So it is ABC triangle. So it is WL by 4. And because it is a M over EI diagram, so you have to just divide it by EI. Okay, up to here it is same. Now the different thing about this is, now this is a conjugate beam. Now see here, conjugate beam, CB means conjugate beam. So conjugate means we are going to replace the supports. Now I can check here, A is a simply support, B is also simply support. If A and B both are simply support, now we'll check this out. According to this table, okay, now see this, actual beam, conjugate beam. Simply support in actual beam remains simply support in conjugate beam. Likewise, roller support in actual beam remains roller support in conjugate beam. Okay, so now we're drawing the conjugate beam. So it is the simply support here. These are simply support. So simply support in actual beam. So this is the actual beam. Simply support in actual beam remains simply support in conjugate beam. So for this bending moment, that is M over EI diagram, we are going to draw conjugate supports here. These are conjugate supports. Same M over EI diagram. I'll just draw. Because it is simply support, I'll just show this arrow here. Here also it is simply support, I'll show this arrow. So now, these are the simply supports of the conjugate beam. Now this is how a conjugate beam looks. After this, what you're going to do is, we're going to find the reactions. Now see here, these reactions are very important. Whatever values you get here for this conjugate beam, whatever values you get this for the supports, they are called as shear force at A, shear force at B. Okay, see here in this first diagram, these are called as the reactions for the actual diagram. For the conjugate beam diagram, when you draw this conjugate support, we're going to write this as VA and VB. So VA and VB, they indicate the shear force of this beam. Okay, now check this out. So see here, since they are simply support, so obviously no change is happening here. Now what we'll find is the reaction. That is, reaction is nothing but shear force. Now you can check this out. Shear force at this point. Now this is the bending moment diagram. All right. So the total load of this bending moment diagram is acting downward. You can see here, load itself is acting downward. So obviously this complete load of this triangle is acting downward. So to stop this triangular load which is acting downward, these two supports will distribute the load upward. So this triangle load is acting downward. To stop this, these two supports in turn exert opposite reactions. So that is nothing but shear force. Okay. Now, see here, if you want to find VA, okay, if you want to find VA, it is the total load which is acting, okay, you can see here, only between A and C. Now see here, only in this portion. So as we know, this is WL by 4EI. It gets distributed equally to left and to the right side. So now this WL by 4 with this area should be calculated. Now if you want to find VA, it is the total load acting, okay, total load which is acting into half of this distance. Okay, now see here. So only this triangular load if you take, so it is half, only this load. Okay, so it is half, this load is acting. See here, this load, I'm showing the load like this here, downward, arrow is downward like this. So this load is acting down, so it is half into base. Base is L by 2, okay, height is WL by 4. So now the total load which is acting downward only on AC portion. See here, AC portion load is carried by VA, BC portion load is carried by VB. And now this is a simple problem because it is symmetrical. So we'll take only this portion load. So this load gets carried over by this portion of the load gets carried by this. Okay. So now RA is nothing but VA is nothing but, when you solve this, again, it is the area of a triangle load, half into, see here, upward load, downward load. Both should be equal. Okay. So it is half into base into height. So half into base is L by 2, height is WL by 4. It is WL square by 16 EI. Similarly, RB also would be same because it is symmetrical. So VA and VB we have got. Now, let's use the formula. So ultimately we have to find slope and deflection. So slope here is nothing but we have to find theta A as well as theta B. So theta A, now it goes like this. The formula goes like this. Theta A, we are supposed to find theta A in real beam. Okay, this is real beam. Theta A in real beam is equal to shear force in conjugate beam at point A. Because we are supposed to find theta A. We are supposed to find theta A. See here, we are supposed to find theta A. That's why we're supposed to find theta A. That's why we'll find this point here, VA. So theta A in real beam is equal to shear force, that is nothing but VA, in conjugate beam at point A. So theta A is equal to, we have already found out VA. So VA is WL square by 16 EI. Now, see here, answer is positive. So it is going clockwise. Now, because it is symmetrical, theta B would be same, that is WL square by 16 EI, but this time it would be anti-clockwise. Now, in case if you're using the sign, so theta B would be minus WL square by 16 EI. If you want to show this direction, you remove this minus sign and show this like this, anti-clockwise. Okay, so now this is slope. We have directly got theta A and theta B. Next, similarly, you have to find maximum deflection, that is delta C. Maximum deflection delta C. So again, delta C, the formula goes like this. Delta C in real beam is nothing but bending moment at C in conjugate beam. So if you want to find theta A, theta is associated with shear force. Delta, the deflection, is associated with bending moment. So theta C in real beam is nothing but bending moment at C in conjugate beam. Okay, so now if you want to find, okay, now delta C, if you want to find this delta C, okay, now check to the left side. So always when you're finding theta and delta, we are going to refer this conjugate beam diagram only. So again, in this diagram, see here, delta C. If you want to find bending moment at C point, check to the left side. Now to the left side, this is a triangle. Check, there are two types of loads. One is this load, okay, and one more is this load, area of a triangle load. Area of a triangle load acting downward. Then VA, shear force, is acting upward. Now if you want to find deflection, it is force into distance. Force into distance. So if you want to find bending moment, so likewise, now check this. So if you want to find delta C, so delta C is to the left side, you see, there is one load, that is WL square by 16 EI. It is acting here into perpendicular distance. So if you want to bind bending moment, force into perpendicular distance. So this is WL square by 16 EI into perpendicular distance, that is L by 2. Now, again, you have to be very careful with the sign conventions. So to the left side, clockwise is positive, anti-clockwise is negative. Okay, so now this is going arrow. Arrowhead is going clockwise. So clockwise it is WL square by 16 EI into perpendicular distance, that is L by 2. Okay, so this is clockwise. Then you can check this. This load is acting downward. Okay, this arrow is acting downward now. Now this load is nothing but half into base. This is the triangular load. Half into base L by 2 into height WL by 4EI. So this is area of a triangle gets converted into a load, that is half into L by 2 into WL by 4 into perpendicular distance. This perpendicular distance, again, centroid of a triangle measured from the base of the triangle is 1/3. So it is 1/3 of L by 2. Now this is going like this. To meet C, it is going anti-clockwise. So anti-clockwise minus. So now when you solve this, you'll get delta C is WLQ by 48 EI. Now again, the approach is different of conjugate beam, but if you solve either by moment area method or conjugate beam method, in both the cases, you'll get the same answer. Okay. The second type of problem is same thing, but this time they've two different points here extra. In addition to theta A, theta B, theta C, the additional points D and E. Okay, determine the maximum slope and deflection. Also find the deflection at 2 meter from left end and 2.5 meter from right support. Okay, so 2 meter from left end and 2.5 meter from the right support. Okay, and again in exam, if they've given you like this, in case if they don't denote the points, so you just add this A, B, C, and extra points you have to add this D and E. Just add these alphabets. Okay, now again it's a simple problem wherein it is uh, AB support. It is a simply support beam with exactly a point load at the center C, that is 30 kilonewton, and you have to find all the deflections as well as rotation. Now you can do this, you'll get to know this only if you draw the deflected shape of the beam. So in this deflected shape of beam, first as usual with respect to A and B, just draw this deflected shape like this. So at A and B, maximum rotation, theta A, theta B. Then below the load at the center, maximum deflection, delta C. Now, in addition to this, though there is no load at D and E, but still it experiences vertical displacement. It experiences deflection at D, deflection at E also. Why? Of course, maximum is at C, but at D and E also there is a deflection happening. You have to find delta D, delta E, and theta D. Because here, if you draw a tangent, see here you'll draw a tangent at this curve, then exactly this point you draw a straight line. Here also you'll get theta D, it's very small, very less. Again at this point, if you draw a tangent, you'll get theta E. And of course, exactly at the center, if you draw a tangent, there is no theta. Theta is 0 at this point. Where theta is 0, deflection is maximum. Where theta is maximum, deflection is 0. Okay, so let's start with this. So after this, drawing the deflected shape of the beam, then you have to draw the bending moment diagram. Okay, now to draw this bending moment diagram, again, because it's a conjugate beam, you have to always, in this method, you have to always use the reactions first. You have to always find out the reactions. So if you find out reactions, you can find bending moment at any given point. Okay, now see here, first find 30 kilonewton, which is placed exactly at the center, that is half of the distance, 5 meter, which is acting downward. So because it is symmetrical, this 30 kilonewton gets distributed equally and to the left and to the right. So 30 kilonewton downward. So to the left, it is 15 and 15. So upward load 30, downward load 30. The beam is said to be in equilibrium. So we found RE and RB. Next, bending moment at C. Now see here, bending moment at C. Okay, so it is reaction 15 kilonewton. So again, to the left side of C, only one load. So 15 into 5. It is 75. So this is a bending moment at C. Next, similarly, bending moment at D. So if you check this again, bending moment at D, again at D, only left side, only one load, 15 into 2. So 15 into 2, 30 kilonewton. Again, left side, all the clockwise is positive. So 15 into 2, 30. Next, bending moment at E. So bending moment at E. Okay, again, now to the right side, there is only one load. It's better to consider to the right side, and right side anti-clockwise is positive. So 15 into 2.5, it is 37.5 kilonewton meter. Okay, so now use these ordinates and draw the bending moment diagram. So this is the bending moment diagram, maximum 75 at D 30, at E 37.5. Next, main interest is conjugate beam. Okay, so as usual, first draw this M over EI diagram. Now see here, it is 30 divided by EI, 75 divided by EI, 37.5 divided by EI. So this is the bending moment, that is M over EI diagram. For this M over EI diagram, we have to make it conjugate beam. So to make it conjugate, again, it is a simply support. So in actual beam, it is a simply support. In conjugate beam also, the simply support remains simply support only. You can see here. This is also simply support. This is also simply support. Okay. So now, just mark this simply support upward and then start this. Okay. Now see here, total downward load. So this is the total load is acting downward like this. So when you draw this M over EI diagram, so obviously this load is acting down. So area of this triangular load, take the area of this triangular load. So it's a triangle, downward load. So total downward load is half into base into height. Okay. So total load half into base 10 into height 75. So half into 10 into 75 over EI. This is the total load which is acting downward. Now, this total load is acting downward. Because it is simply support, it gets equally distributed to the left and to the right. Symmetrical, so to the left and to the right. So total load acting downward is 375. So this 375, it gets distributed left and right. So it becomes 375 divided by EI into half. That is 187.5. So to the left side 187.5, to the right side also it is 187.5. Okay. So after this, in the previous method, it is little different. What we had done here was we had just taken only this portion. We have taken only this portion. This is one way to solve. So what we did was half into base into height. We have taken only this to find VA. Okay, this is another method to find. That is, you can consider the complete triangle half into base, complete base into height. Take this. Now this you have to divide it by 2 because whatever is acting at the center here, that gets distributed to the left and to the right. Okay. So now, so when you solve this, so we'll get this V and VB, which are nothing but the shear forces. So theta, we have to find theta A and theta B. So first let's go with theta A. So again, write the formula. Theta A in real beam is equal to shear force in conjugate beam at joint A. Okay, now shear force you have already found out. Okay, so theta A is nothing but 187.5. So again, answer is positive. So this is clockwise. Similarly, theta B is just the opposite, minus 187.5 or EI. Now this is anti-clockwise. Okay. Next is delta C. We have to find this delta C, maximum deflection. Again, the formula is delta C in real beam is equal to bending moment at C in conjugate beam. Delta, again, theta is associated with shear force. Delta deflection is associated with bending moment diagram. So theta C in real beam is delta C in real beam is equal to bending moment at C in conjugate beam. Okay, again come to this point, bending moment at C in conjugate beam. So at C, now check again to the left or to the right. You can check either of this. Okay, so to the left, if you check delta C, okay, delta C to the left side, there are two loads. This is one load, and this area of this complete triangle is another load. Okay, now you can check this delta C. Delta C is nothing but we have to find bending moment. So it is force into perpendicular distance. Then this triangular load, which will convert it to one single point load, that load into perpendicular distance. So delta C is 187.5 into total distance, that is 5 meter. So again, it is going clockwise. So positive. Next, this complete triangular load, okay, because it is maximum at the C. So we'll take this complete load. We'll ignore this 30 over EI. We'll treat this as complete one single triangular load. Okay, this load, okay, area of this load. So area of this load is acting downward. So it is half base 5 meter, height 75. So this area gets converted into point load, which is acting downward. Then its perpendicular distance. Okay, now this here, again, we are measuring at C. The centroid of a triangle measured from the base of the triangle is 1/3. So it is 1/3 of 5. Okay, so we're taking, just a moment. Okay, so what I meant to say was, we are considering this complete triangle. You can see here. So this complete triangle, I'm taking AC, this portion. This complete triangle I'm using, which is acting downward. So area of this triangle is half into base into height into CG distance. CG distance is, again, we're measuring from this point. Okay, so it is CG distance. Okay. All right. So 187.5 into this distance, it's area of this into CG distance. Okay. When you solve this, again, be careful with the signs, clockwise positive, anti-clockwise negative. Okay. Next thing, again, they've asked us to find out, also calculate reflection at 2 meter from the left end. So 2 meter from the left end is delta D and theta D, delta D and theta D, and theta E and delta E. Okay, so the first thing is calculate the slope and deflection at D, that is at 2 meter from the left end. Okay, use the same formula, theta D. So if you want to find theta, theta D in real beam is equal to shear force in conjugate beam at point D. You can see, just check this in this conjugate beam diagram. Again, we're going to find at this point at D. So theta D is nothing but, we have already calculated this. Theta D in real beam is equal to shear force in conjugate beam. In this diagram, we have calculated only V and VB, but there's additional step, that is D. So if you want to find out D, only you have to consider this triangle. Now to the left side of D, check only the forces, because shear force deals with forces, bending moment deals with force into its perpendicular distance. So theta D. So theta D to the left side, see here, theta D to the left side of D, there are two forces. One force is acting upward, that is VA, 87.5. We've written 87.5. Again, left side upward positive, downward negative. So left side upward positive, that is 187.5 plus. Again, it is a M or EI diagram, so divide it over EI. Next, take the area of this triangle, only the area of triangle of this AD up to A and D. So VA is acting upward, positive. Area of this triangle, which is acting downward. So area of the triangle is half into base into height. So half, next base is 2 meter, height is 30 over EI. So it is minus half into base into height. Again, that load is acting downwards. That's why we're considering it as negative. When you solve this, you'll get theta D. Again, theta, shear force. So only the forces. Take only the forces. Next, delta D. Delta means, again, it's a bending moment. So write the formula, delta D in real beam is equal to bending moment of conjugate beam at point D, same point. So delta means, again, bending moment at D. So it is, come back to this point. Okay, so it is bending moment at D. Consider to the left side. So V is acting to the left side. So V is 187.5 into its perpendicular distance into 2. Again, left side, this is clockwise. So clockwise is positive. Then area of this becomes negative, which is acting downward. So this area of this triangle becomes the load here, downward load. So it is again half into base 2 meter, height is 30. Now it is acting, you're measuring from D point here. So if you're measuring from D, again, the centroid of the triangle measured from the base of the triangle is 1/3. So this is 1/3 of 2 meter. So it is 1/3 of 2 meter. So now delta D is, solve this, simplify, so you'll get this answer. Likewise, you have to carry out the same step for theta E, to find out theta E and delta E. Now to find out theta E, which is acting at a distance 2.5 meter. So it is acting at a distance 2.5 meter from point B. So again, theta E, if you want to find out, you have to consider only this triangle. Now again, to the right side, okay, again the sign conventions, to the right side, upward is negative, downward is positive. Okay, so we have used the same thing here. To the right side, right side, upward is negative, upward negative. So only one upward force is acting here, the right side of E, that is 187.5, upward negative. Then downward, again take this area of this triangle. So it is again half into base 2.5, height 37.5. So you have to consider only the forces here. So it is minus 187.5 plus this parameter. So simplify this, you'll get answer negative. So again, it is in radian. Okay, so theta E is negative. Similarly, find out delta E. So delta E in real beam is equal to bending moment at E in conjugate beam. So delta E is equal to, okay, again, right side, actually there's a problem. Okay, right side anti-clockwise is positive. So it is 187.5 into 2.5 meter. There's a little correction here. So it is plus 187.5 into 2.5 because right side anti-clockwise is positive. Okay, into 2.5 over EI. Next, then there's a downward load. So downward load is, again, right side clockwise is negative. So area of this. So just change the sign here. So this becomes plus, this becomes minus. Okay, so again it is half into base into height. Same thing, half into base into height into this distance, CG distance. Again, centroid measured from E. You have to measure from E. So centroid of the triangle measured from the base of the triangle is 1/3. So this is 1/3 of 2.5. So again, when you solve this, but you solve this right, because one becomes plus, the other becomes minus. Just ignore this. Use just the moment, that is clockwise and anti-clockwise sign conventions, and then find delta E. Whatever is the answer, solve this properly. Just keep it here. That would be delta E. Okay. Now we can notice here, theta A and theta B are maximum. Theta A is positive. If theta A is positive, theta B is negative. It is just the opposite. See, theta A is positive, theta B is negative. Likewise, delta D is positive, theta D is positive, whereas theta E is negative. You can see here, theta to the left side of C, theta D is positive, theta E is negative. So to the left side of C, they are all positive rotations. To the right side of C, they are all negative rotations. And of course, you'll get maximum delta at maximum deflection at C. At D and E, they comparatively lesser. Okay, so in conjugate beam method, the first thing is drawing this deflected shape of the beam, then bending moment diagram as usual, followed by M over EI diagram. Okay, so after this, in conjugate beam, you have to replace the actual supports with the conjugate supports. So in simply support, things are simple because simply support remains simply support in conjugate beam also. Whatever is there in the actual beam, the same simply support is maintained for conjugate beam. And then you can just go on solving with this. So the approach is different, but ultimately if you solve either by bending moment moment area method or conjugate beam method, both the ways you'll get the same answer. Okay, thank you.